Hello everyone, and welcome back to Reverse Engineering Linux 32-bit Applications. In this video, we're going to talk some more about stack buffer overflows. So we've been talking about these for quite a while now, which isn't bad. Again, these are very common flaws. So we're going to learn everything we possibly can about these flaws. Now, today, I want to talk a little bit about ASLR mitigation. So you might say, well, what is ASLR? Well, we've mentioned this briefly before. And this stands for Address Space Layout Randomization. This is the thing that we turned off earlier. We said we were going to attack some of these issues one at a time when it came to attacking our vulnerable applications. So what does ASLR do? This randomizes the location of the stack, also the heap. The heap is where you allocate memory if you're not using automatic variables on the stack, and also shared libraries. So in some previous videos, we used return to libc. We said, I know the address for a function in libc, so I'm just going to go ahead and call it. Now, we were able to do this because we knew the exact address. Now, here's the problem when you're using ASLR. You do not know the base address for the library. That is now an unknown. It's been randomized. However, the offset into that library is still unchanged. So all we need to do is somehow figure out what the base address is, and then we can go from there. So this is an interesting problem, and there are a couple of solutions. Now, the solution that I'm going to talk about right now actually doesn't require you to know this base address. And that is to use something called procedural linkage tables. And I'll go over that in a little bit more detail shortly. You can also overwrite something called a global offset table. So these are two good options. If you're desperate and you can inject the proper code, you can do some sort of brute force attack where you try to figure this out. All right, a little bit more about procedural linkage tables. So when you have a shared library, shared, okay, sounds like you're sharing with some other folks. Well, those other folks are other programs. So a shared library will load itself into memory, and the code segment, which is the text segment, is shared among all of these programs. So each program has its own private data segment. So if you look at the data segment of a shared library, you will see that it is, in fact, not common to all of the different programs. This allows each program to have its own version of global variables, etc. Now, the code in a shared library is what we call position independent code, or PIC. Not pilot and command if you're an aviator, but in this case, PIC means position independent code. What does this mean? So if you look at the code in your program, you might see calls where it says jump to this address. Well, you're not going to see that in position independent code. Rather, instead of having these absolute jumps, you'll have relative jumps. Jump forward this many bytes, jump backward this many bytes. Those are the kinds of things that you will have. If you think back to when you were first learning programming, sometimes they said jumps are bad, right? So some languages will support jumping, and they said you can use this, but don't ever use this. So it's kind of similar here. When you compile this library code, you have to make sure that it is compiled into code that doesn't care where it runs from. And that is your shared library code. Now, these library functions are not called directly. Instead, we have a stub in the PLT, the procedural linkage table. All this does is it says, oh, you wanted to call printf, for example, or stir copy. Let me go ahead and look up that address for you. I'm going to use the dynamic linker to find this thing. Once I've found this thing, I am going to write its address into something called the global offset table. So the global offset table, or GOT, contains the address of this library function. So what does this mean? This is what it means. I can use the PLT in order to call my function. I don't have to know the absolute address. So you're thinking, wow, this sounds pretty cool. What are the limitations of this? Well, here's the biggest limitation. If you did not call this function in your program, it's not going to be in the PLT. The PLT doesn't have a list of every single function in every shared library that has been linked. It only contains an entry for functions that were used by this program. So let's go ahead and have a look at our program. Let me just bring it up here. I'll use my testy script. It doesn't really matter for our purposes because we just want to look at the code. Then I'll go ahead and run to my first breakpoint, and I will analyze it as usual. And so now let's have a look and see what's going on here. Here when I call stir copy, I'm not calling stir copy in my shared library. Rather, it says call buffer overflow stir copy at PLT. So here I am using this PLT code. So what does that tell me? Well, let's have a look at this. Let's watch this run. Right, so I'm going to set a breakpoint right here. And I'm going to run to that new breakpoint. And I'm going to step in. It says call buffer overflow stir copy PLT. And here it is. I've gone to this address, 080482E0. So what does that mean? If I wanted to exploit this, now I only called strcpy here. I didn't call something useful like system or exit in this program. But again, this is a very small, just example program. So now I have the ability to jump to this address. So I'll just go ahead and I'll just copy down this location is 0804. And again, you do not have randomized code addresses for your actual program, E0. So now I can go back out. Let me close this. And I will do a sudo echo 0 to proc. First, let me just verify that this is still set to 0. And now I'm going to do a sudo. I could try it without the sudo. I'm going to echo 2 to proc sys kernel randomize VI space. And it says permission denied, of course. Should have used sudo, not su. I don't know what I was thinking. All right, now I'll exit here and I'll rerun my cat command and just verify, yes, this has been turned back on. So now I have ASLR being used. Let me go back and run my program again. Run to my breakpoint, analyze, go here, set my second breakpoint, and run to that. I will step in, and sure enough, if I look at my notes, this should be 080482E0, and it still is. It is still that location. So it's going to go ahead and call the appropriate function. If you wanted to, you could trace through this a little bit. So I could say, all right, I'm going to jump, push, 0. Going to jump forward. So here I'm pushing some values. And now I'm going to call this function, F77665E0. If I jump into that function, I will say, well, what does this look like? And if I step through this, again, I could analyze this region, and I can step. So there's a preamble. I'm going to call this function, and on we go. So this is basically stir copy that I've managed to step into. Go ahead and let it run. And then, of course, it had a problem. And what was the problem? The problem was I still have this old address, F7E3B940. That is what I injected with my little testy script. And so it said, hey, that's a bad address, because that's what it ended up returning to. So if you don't believe me, I can go ahead and pull up this script. And here it is. Here's that address, F7E3B940. So what would I put in its place? I could put in its place just the address for the stub. Now, what if that one function call wasn't sufficient? Guess what? You could do something like what we did in a previous video when we chain together calls to libc. So what you can do in this case is you chain together calls to these different functions. So this is a pretty cool technique. Again, the biggest limitation with this particular technique is that you can only call things that were referenced in your victimized program. So a very small program like this one, there aren't a lot of things to victimize. However, in a larger program, if they have things like they're going out to the shell to do something, so they have system calls and calls to exit, then you're golden. You can do all kinds of great things with that, especially if you have the appropriate permissions. So if you have the permissions for the program itself, maybe you're lucky, it's running as root, then you're going to be really happy. Maybe it's not. So there's a lot of fun things that you can do with this. So this is just one technique that you can use to bypass ASLR. And there's some other techniques that we will likely cover in some future videos. But that is essentially all I wanted to talk about in this video. Now, as a reminder, this video is one in a large family of video courses that we have here at Pentester Academy on everything you ever wanted to know about InfoSec, but you were afraid to go somewhere else and spend a lot of money to learn. So you can come to Pentester Academy. It's very affordable, and you can learn everything you need to know in order to be the best InfoSec professional that you could possibly be. So I look forward to seeing you in this course or another course soon. See you then.